You know when you're in your terminal and suddenly it just bursts into color? Or you see this super smooth progress bar. It feels so modern, right? Well, what if I told you it's all powered by this surprisingly old but really clever technology that basically turned plain text into a digital canvas?
I mean, really think about it. You see this stuff all the time. Your code editor screams at you with bright red syntax errors, you pop open a system monitor like HTOP, and you've got green and yellow bars showing CPU usage. Or maybe a build tool is chugging along with a nice little progress bar. All of that is happening inside what is, at its core, just a simple stream of text. That's it.
So that's the big question, right? How in the world does a text-only screen pull off these rich, graphical-like displays? How is it even possible? Well, the answer is this absolutely brilliant standard that came along and brought some serious order to what was for a while total digital chaos.
Okay, so to really appreciate the solution, we've got to go back in time and look at the problem. Because in the early days of computing, the world of text terminals, well, it was basically the Wild West. See, every single manufacturer, I'm talking DEC, Hazeltine, all of them, they all spoke their own different language. They had their own secret set of commands to control their hardware. So if you wanted to do something super simple like just move the cursor, you had to know the specific secret handshake just for that one model of terminal.
And this slide just nails the problem perfectly. Look at this. To move the cursor on a DEC VT100, you're sending escape, then Y, then the coordinates. Simple enough. But what about on a Hazeltine 1500? Oh no, that's totally different. You're sending a tilde, a completely different control character, and the coordinates are separated by a comma. It was a complete and utter mess. We're talking about a digital Tower of Babel for developers.
So this chaos meant programmers had to build these huge, complicated translation libraries. One of the famous ones was called termcap. So a program couldn't just talk to the terminal. No way. It had to talk to termcap first. And then termcap would act like a translator, looking up the right, obscure command for whatever terminal you happen to be using. I mean, sure, it worked, but man, was it inefficient.
But out of all that frustration, something amazing happened. A beautifully simple, totally elegant solution came along. A universal language that pretty much any terminal could understand. And this, my friends, was the birth of the ANSI standard.
So here's the big idea. ANSI escape sequences. And they're basically just special little strings of characters, these codes, that you stick right inside the text you're sending. Now here's the clever part. When the terminal sees one of these special codes, it doesn't print it. Nope. Instead, it reads it as a command, a secret message, kinda. Like, hey, make the next word red, or, okay, clear the whole screen now.
Now, the idea was kicking around as early as 1976, but the real game changer, the thing that made it all stick, was the DEC VT100 terminal, which came out in '78. It was the first really popular device to support these new codes, and it was a monster hit, a total commercial success. Suddenly, everyone started making VT100 clones, and since they all had to be compatible, they all supported the ANSI standard. And just like that, it became the default language for terminals everywhere.
All right, so let's get our hands dirty. Let's pop the hood and see what these codes actually look like. How does a simple string of text tell a terminal to do something like make the next words bold and red? Okay, check this out. It's actually a pretty logical structure. Every single command kicks off with an escape character. That's the hey terminal, listen up signal. Right after that, you get a left bracket. That's the control sequence introducer, or CSI. Then you get the parameters. In this case, 1 means bold and 31 means red, separated by a semicolon. And to finish it off, you have the letter M, which tells the terminal, okay, this is a command to change how the text looks. Simple, right? It's like a little 4-part sentence that any compliant terminal can understand.
So once this new grammar was established, developers could suddenly do something pretty incredible. They could paint with text, and this is where all that beautiful color comes into play. Now at first, the standard was pretty modest, you know? It only defined 8 basic colors for the text itself, that's codes 30 through 37, and another 8 for the background, using codes 40 to 47. But you have to remember, coming from screens that were just green or amber text on a black background, this was absolutely revolutionary, a huge leap forward. But of course, developers are going to be developers, and they immediately found a clever little hack. They figured out that on a lot of terminals, if you applied the bold attribute, code number 1, it didn't just make the font heavier, it also made the color brighter. So just like that, regular red, code 31, could become bright red, and boom, they'd effectively doubled their color palette to 16 colors. So clever. And that 16 color palette was pretty much the standard for a good long while. But technology doesn't stand still, right?
Things escalated pretty quickly. As graphics hardware got better and better, the terminal's color abilities just exploded, going from that initial 4-bit color to 8-bit, and finally to the 24-bit color we see in modern terminals. That jump to 8-bit color was a big deal. It gave us 256 options to play with. So you got the original 16 colors plus this big 216 color cube, which is basically 6 shades of red times 6 of green times 6 of blue. And you even got a really useful 24-step grayscale ramp. For a lot of years, this was the absolute sweet spot for terminal apps.
And then, well, we hit the modern era. Today, most terminals you're using support 24-bit true color. We're talking over 16.7 million colors. It allows you to specify a color directly with its RGB values. To put that in perspective, that is the same color depth as the photos and images you see on the web every day. And it's all done with simple text commands. Just mind-blowing.
So at this point, you might be thinking, okay, cool history lesson, but so what? We live in a world of slick graphical interfaces and high-res screens. Why on earth should we care about a text-based standard from the 1970s? Why is it still so important? Well, get this. Here's a wild fact for you. For decades, the Windows command prompt completely ignored ANSI codes. It had its own weird proprietary system. But then, in 2016, with Windows 10, Microsoft finally threw in the towel and added full support. Now, why would they do that? Because the entire modern world of developer tools and open source software relies on it, especially with things like the Windows subsystem for Linux. They literally had to adopt this 40-year-old standard just to stay in the game. When it comes right down to it, these codes are the invisible engine that powers so much of a developer's day-to-day work. The syntax highlighting in your editor? ANSI codes. The colorful file listings when you type ls? ANSI codes. Those progress bars, the dashboards in HTOP, the readable logs that make debugging even possible? It's all powered by these simple escape codes. They're what make our text interfaces not just usable, but actually intuitive and incredibly powerful. And that just makes you wonder, doesn't it? Here's this elegant, simple solution from the 1970s, and it's still humming away right at the core of our most advanced software tools today. It kind of makes you think, what other invisible foundational technologies from the past are still quietly running our modern digital world?